To turn a digital wireframe into a physical product you can actually sell, you have to bridge the gap between software and reality. Slicing software establishes the model's structural strength, the total print time, the exact material usage, and the overall risk of a failure during production. To get this right, you need to lock in the correct hardware profile, dial in the exact strength parameters, strip out unnecessary waste, and scrutinize the final digital preview. By taking the time to engineer one flawless digital build plate, you create a verified blueprint, and that blueprint is the foundation for scaling up an entire print farm. Before you touch a single internal setting, like wall thickness or infill, you have to define the physical environment. Look at the top left of your slicer. You must select 4 specific variables first: the exact printer model, the nozzle size, the build plate type, and the filament material you plan to use. If you import a downloaded 3NF file, do not assume the designer's presets match your specific equipment. A file sliced for the wrong nozzle or plate can cause terrible layer adhesion and inaccurate time estimates. Confirming these physical constraints right from the start ensures the software is doing the math for the actual machine sitting on your desk, keeping your production run on schedule and intact. A printer spends minutes heating the bed, leveling, and prepping before laying down plastic. By cloning a verified model and arranging multiple copies on the same plate, you spread that dead startup time across a larger batch of sellable products. But packing every available square inch is a calculated risk. If you have 30 fragile items on a crowded plate and one detaches on hour 12, the loose piece can collide with the tool head and wipe out the entire batch. Always check your layout for physical clearance. Parts should never touch, hang off the grid, or encroach on the exclusion zones near the edges of the bed. Arranging a build plate is a manufacturing trade-off. You are constantly weighing the benefit of maximum throughput against the financial cost of a single mechanical failure. This diagram shows our baseline standard for most merchandise production: a 10% gyroid infill pattern surrounded by 3 outer walls. Increasing that infill percentage uses extra material for very little structural gain. Instead, adding outer perimeters creates a rigid shell that absorbs impact and strengthens joints. For standard PLA filament, set the outer wall speed to 150 millimeters per second. The less visible internal features, like the infill, can run at 250. There is one major exception. If you are printing on an effects plate, like the Galaxy Star surface, or if the model has a very tiny footprint, you must drop the first layer speed down to 30 millimeters per second to guarantee the plastic grips the bed. Think of a heavy stand mixer. Aggressive, rapid motion will tear delicate ingredients apart, while a slow, gentle sweep keeps the structure intact until it is strong enough to hold up. When printing multiple colors from a single nozzle, the machine has to push out the old filament before starting a new color. This is called flushing, and it prevents the colors from bleeding into each other. This chart shows the flushing volumes for different filament swaps. By lowering the default global multiplier from 1.0 down to around 0.6 or 0.7, you drastically cut down the amount of plastic purged into the waste chute. However, high contrast transitions require manual adjustment. Switching from black to white needs a much higher flush volume to prevent the white layers looking gray and muddy. Conserving filament is a smart business practice, but it only works if the final item meets the quality standard. A plastic toy with muddy color bleeding is a wasted print, no matter how much purge material you saved. Here is a comparison between the standard model view on the left and the sliced preview on the right. The standard view is an idealized, smooth surface. The sliced preview is the physical reality, showing the exact toolpaths the machine will follow. Inspect those toolpaths carefully. Verify that thin features like claws or hinges survived the slicing process. Check that the visible seams are hidden on the back of the model, and ensure the correct color is mapped to the right layers. Pull the vertical layer slider all the way down to layer 1. Look closely to confirm the model has a large, continuous contact area with the build plate to prevent it from knocking loose. If a feature looks broken, separated, or floats in mid-air on your screen, it will fail in the machine. The printer only executes the code it receives. Treat the sliced preview as the final, non-negotiable checkpoint to catch hidden manufacturing defects before committing hours of machine time and raw materials. Once the preview is verified and the first layer tests successfully, the digital model functions as a finalized manufacturing unit. Now, when you need 50 more copies to meet customer demand, you don't rebuild the layout from scratch. You take that one verified plate and duplicate it across as many printers as you need. Applying strict hardware selection, deliberate strength profiles, and rigorous preview checks removes the guesswork from the process. It takes a chaotic hobbyist tool and turns it into a predictable, highly efficient production line.